Okay, so here's our box, and what we are imagining now is that we have a photon that's emitted at one side of the box and then is absorbed by the other side of the box. Okay, so it's going from left to right within the box. Okay, now when the photon is emitted from the left side of the box, okay, it has an energy E. Okay, so the photon has an energy E. Okay, and so it carries a momentum E over C. Okay, and so in order to conserve momentum, then three momentum, then when the photon starts to move from left to right with momentum E over C, then the box has to get a kick to the left, and so it has to acquire velocity v. Okay, and this acceleration actually happens very quickly, and it happens once the photon somehow has been emitted, then this velocity v has been acquired, and since it's frictionless, then the velocity is constant. Okay, so the momentum of the box the momentum that the box acquires via this recoil from the emission of the photon. Okay, so the box has momentum mv, and it has to be equal to minus E over C. Okay, now it's okay. We're going to assume here that the energy of the photon is much less than the rest energy of the box, and what that means is that the velocity is going to be low. It's going to be non-relativistic. So we're just using the non-relativistic expression for momentum instead of gamma mv. Okay, so basically gamma is equal to 1. All right. So so this is the momentum that the box acquires when the photon's emitted. Okay, and then when the photon is absorbed, then it must stop. Okay, the box will acquire a momentum kick in the opposite direction of the same magnitude, which brings the box to a stop. Okay. Okay, so now if we consider that if we designate the time between the photon being emitted and being on the left side and being absorbed on the right side, right? It takes some time for the light to travel. It's not a long time. If we call that delta t, okay, then the box in delta t, then the box moves a distance delta x sub b, okay, which is equal to v delta t, and we can just get v from here. It's just minus E over c over mc. So this is equal to minus E over mc delta t. Okay, so that gives us how much the box moves during the time that the photon traveled from the left side of the box to the right side of the box. Okay, in that same amount of time, delta t, then the photon moves how far? Well, it moves its velocity times delta t. Okay, and the distance that it moves is the length of the box minus the distance that the box moved. Okay, this should all make sense. That looks really messy. Let me clean that up. Okay, so so once the photon gets absorbed at the right side, then the box stops because it gets a momentum kick to the right in the opposite direction of the same magnitude, and so the box stops. The photon's absorbed, and so the box is moved, and it's moved this amount of this distance.